Okay. So last Wednesday we got to hear in our description of the physics of CT imaging, and we'll continue looking at how the physics works and how the reconstruction works as well. A number of you, if you've taken 280A, this will be a review because we covered it fairly extensively there as well. If you recall, this is the volume that you can achieve on a scanner that has a 16 centimeter field of view. So we go right from this is the apex of the left ventricle here. And as we move towards the patient's head, moving up through the heart to the mitral valve and the left atrium is here. This is the left ventricle. It's going to eject the blood out this pathway, which is the aortic outflow tract, which is right here, right? And then here's the aortic valve. Coronary arteries coming from the cusps of the aortic valve come out here. There's the right coronary, which is emanating from the just above the aortic valve. And then the big left main vessel comes off here and then goes to the left anterior descending and then also wraps around here as the circumflex. So the entire heart is basically sampled. So here we have pulmonary veins going into the left atrium, which is below it. This is the ascending aorta, right? And this is the descending aorta after it goes around the aortic arch. And so we have essentially the entire heart captured with one full spin of the CT scanner, making it an extremely powerful cardiac imaging technique because you can do it so quickly. Looking at some of the hardware that's out there, this is I think this is a Siemens somatome. We looked at the slides for the GE. That's at this website. We can look at this thing spinning. If I get out of this, how do I get out of here? We'll watch this video quickly. This is engineers have taken the covers off this scanner and they've just started it up. This is a Siemens somatome flash, and so you can see it's encased in this stuff. It starts spinning. We can go ahead a bit, spins up faster. Now it's really booking, right? So this thing goes about 3 revolutions per second or maybe 4. Excuse me. Great thing is look at the paper that's on the patient table. It's getting blown all around like this is a big fan. And on the soundtrack, the engineers are kind of laughing to themselves, but so this is, a lot of mass to be spinning in. And so there's a good reason why companies like Siemens and Philips and GE make these machines, right? Because they're large pieces of engineering that require high tolerances. So the barrier to entry to make one of these scanners is fairly high. If you wanted to start your own company, which is your own CT company, one, you would have to license a lot of technology that is just basic to the industry. And 2, you have to have a manufacturing capability to make stuff like this. Okay, so let's go back here. Excuse me. So that's the manufacturer videos. They're in the slides, so you can look these up for entertainment purposes. And some of them are quite informative. Shut this down, put it over here. Siemens came up with a very interesting design and proposal. Instead of making the detector, say, 256 slices, they kept it at 64 at that generation, but they put 2 of them inside the gantry. And so they have a main tube and detector here, and then this other one, it's the same tube, but the detector is a little shorter, but it's at 90 degrees to this one. So this is really terrific, right? You get a lot more angular coverage, and it cuts down your scan time by close to a factor of 2. right? So now, in order to take an image of a heart, you basically only need 66 milliseconds, right? So the question, the obvious question is, well, why go that fast? 66 milliseconds seems really fast. The heart's pretty well always in motion. There's two times where it has the least motion. One is when the ventricle has refilled with blood and it's relaxed before the next contraction. That's called end diastole, and that there's some drifting motion, slow drifting of the various components of the heart, but the total displacement is in the millimeters range. And then after the heart contracts and it's reached its maximum ejection of blood, and so the left ventricle is the smallest, that's called end systole. And there's usually anywhere from 50 to 100 milliseconds at end systole where the heart is basically motionless, like the motion's within a millimeter or two at any point. So at those 2 points, if you can capture your entire image in either one of those windows, then you will be far less susceptible to motion artifacts, blurring and ghosting and things like that, and streaks from the motion artifact. So that was their idea. They were going to go, they did go this way. The unfortunate part of it for cardiac scanning is that because there's only 64 slices and it's, say, an 8 centimeter throw or even less, 6 centimeters, something like that, you can't get the whole heart in one heartbeat, right? So if you want the entire heart at end systole, it's going to require 2 to 3 beats, and you're going to have to shift the detector or the patient through the detector and sample 3 different end systolic states and paste those together like they were one, right? And this is what's done in echo, it's done in MR all the time, is you take multiple beats and cobble them together to pretend there's a single beat, which is fine if the person has a very even rhythm, right? So their EKG shows an R to R interval that's reproducible within, say, 5% or something like that. The other thing is that the heart itself can be undergoing a slow change over time, like the heart rate can be changing slowly, or they can throw a single bad beat into your soup. So if they have an ectopic excitation, or a skipped beat, sometimes, as you would call it, then if one of the 3 heartbeats used for making the images is that skipped beat, the whole thing looks like a mess, right? So there's big chunk of the heart that just looks quite different. So this is not my favorite design for cardiac scanning. I prefer the single detector that gets the whole heart in one go. In order to, we talked about this a little bit last lecture, in order to achieve enough X-ray detection in, say, 66 milliseconds or 140 milliseconds, you need a very bright X-ray tube. There needs to be a lot of X-rays per unit time coming out of that tube. And so over the years of CT, this is pretty well the entire history of CT. This shows, where we are in sort of the kilowatt output of an X-ray tube, right? So if you think of a light bulb, it's like an X-ray light bulb. And now the modern ones are putting out 100 to 120 kilowatts, right? So it's basically, if you flip the switch on and off, it's like flipping on 1,000 100-watt bulbs, right? So if you tried that in your house, it wouldn't work, right? You'd blow the fuse. So you need a special power generator for this. And you need to be able to withstand the heat that's generated with the bombardment of the target to make that many X-rays. And so this technology has tracked with CT as well. And for example, we are at this point waiting, because this upgrade is so popular for our scanner that we have, we're waiting on the new X-ray tube for the scanner that we have over in the Jacobs Hospital. And it will essentially double the amount of X-rays that are coming out, right? And that upgrade obviously isn't free, but it's well worth it. Here's an example of data that's obtained from 3 EKG leads that are placed on the patient while you're obtaining their CT data. And while they're lying on the table, you can see their EKG on the screen. This patient obviously has not a steady heart rate. Okay, their heart rate is not steady. The number here gives the heart rate that you would observe if this was the R to R interval. Okay, so it's 112 beats per minute if that's the R to R interval. Then that interval gets longer, so that's a 90 beats per minute, 79 beats per minute, etc. So this is going all over the place. Not a good situation if you want to combine heartbeats into one image. And so you would need to, if you had a CT scanner that required multiple beats, you're going to wait until this settles down. And you're probably going to give the patient some kind of pharmaceutical to settle down their heart. Again, with this new tube and a faster gantry, essentially you can get everything done, the whole volume, in one heartbeat. So you just pick, it doesn't even matter which beat you pick almost, right? So in the diagram that we're showing here, right, we've just said, okay, fire when I see a QRS. I know at a 300 millisecond delay, I'm going to be in end systole after that QRS or somewhere close to that. So I'll just scan during that time and I'm done. And so you didn't have to wring your hands about whether or not the heart rate is steady. What the maximum rate you can achieve and still scan is still being determined, right, for these new tubes. And it's probably 120 beats per minute, something like that, to get good quality pictures. What's shown here is, this is data for an image that was reconstructed with the data that was obtained across this time width here. This gray box tells us, actually, you have data for this entire time width here. So you can reconstruct multiple pictures with different temporal offsets. So I could take this purple window and I can just pass that window across the bigger window that I have data and just create images that are time delayed. Right? And so in that sense, you can make a movie of what's occurring across this R to R interval. Obviously, the width of this makes that movie a blurred movie in the sense that, you know, each frame in the movie is a compendium of data from a temporal width. But it looks pretty darn good. And so here's another example of just, you know, a random study pulled off the scanner. There's nothing special about this scan. But you can see the clarity with which these tiny little calcium granules in the coronary artery are visualized. I mean, that's a pretty small thing, and it's got a pretty sharp edge, right? To determine where it is and how big it is. And then, you know, we look up here, same thing. You have these very detailed little calcium bits here, little vessels coming off the main vessel. So they, you know, when everything works out, it's a pretty special picture. So we're going to look at reconstructing these images and how the projection data is used to reconstruct the images. Before we do that, we'll review how X-rays are attenuated by materials. And so if I have a material here, let's say this is a slab of water, right? And 1,000 X-rays hit this slab of water, and I measure on the other side here, 800 came out of the material. So 20% of them got absorbed inside that material, right? If I put an equivalent slab or the same geometry and the same material here, I know that when the X-rays hit this, 20% of those X-rays will get absorbed. Okay? So the 800 becomes 640. The 640 that hits the next equivalent slab, 20% of those will get absorbed, and so I get 512. So this type of attenuation fits this model exceptionally well. You can derive this equation in multiple ways, but we're just going to go straight to the solution, which says that the number of X-rays I see at any depth X through a material is proportional to the number that went in times an exponential decay, which is proportional to the depth at that, X, how far in the material are, and a physical constant / coefficient that is dependent on the atomic structure of the material. And so materials that have a big electron cloud, for instance, so high Z number materials will cause a lot of collisions between the X-rays and the material, right? So iodine, for instance, this mu value is a very big number, and so this decay as I'm moving through the material is very quick, right? So it happens very quickly. For all of the data that we're looking at, we assume this is occurring through all of the materials we're looking. There will be some artifacts introduced because it turns out that this material is preferentially going to attenuate lower energy X-rays. So if these X-rays go, hitting the material aren't of identical energy, they're a spectrum of energies, the lower energy X-rays get attenuated at a higher percentage than the higher energy X-rays. And so the spectrum at each step here changes, and it starts shifting towards higher mean value of energy. But we're actually going to ignore that for the most part, and unless you have something that is highly attenuating or causes this beam hardening, it's called, such as a lot of X-ray contrast dye or something like that. Most of the time you can ignore the effect. Well, let me rephrase that. Most of the time that effect is easily correctable. That's what I'm going to say. It's not ignored, but there's a simple correction as opposed to some complex model-based thing. So let's look at the geometry of what we're looking at here. This is very much like SPECT, and we went through this once before with SPECT. You recall in SPECT, there was a photon created inside the patient, and it emerged from the patient and hit our detector. And so this cartoon is the mathematical description of this detection of parallel lines of radiation through the patient. In the case of CT, we have a source of X-rays up here, right? We're assuming mathematically what we're going to look at are the parallel rays, right? And so one way of saying, well, how could that happen, is I have a source that shoots X-rays down this way, and then I raster that source across the sample. And that's how CT imaging was originally done. Now it's done with a source, and then a fan beam comes out, and you have to resort the X-ray beams such that you get a bunch of beams that are all parallel when you're constructing this data. What the data is, excuse me. So I have a source of X-rays coming in here, hit the patient, and I'm going to say I have a flux of X-rays of intensity I0 that hit the patient. And then the question is, what is the intensity of X-rays that hit my detector or emerge from the patient, let's say right here? Well, it's whatever it was going in, attenuated by some percentage, right? Yeah.
So how do we know what's going in? Is that like a nominal value, or is it calculated by the machine?
That's a really good point. So the question is, those online can hear, is like, how do you know this value? right? I naught. Like how do you know what that intensity is going in? And the machine is calibrated such that when you set two variables on the machine, you set the kilovolts, peak on the X-ray tube. So that can range from say 70 to 140 kilovolts peak. So that sets the kind of spectrum of X-rays you get. And then you can dial up the current that is the electrons hitting the target. So if I say have my current at 100 milliamps, so it's 100 MA, then so many electrons per unit time will hit the target, so many X-rays per unit time come out. I can double that to 200 and I get twice as many. And so in the morning, basically what happens is every day they turn the X-ray tube on, warm it up because you need to get it warm and everything like that. And then they step through different MAs, different intensities, and they step through different energies and they calibrate the whole thing. So that now when I push the darn button and say I want, 120 kVp, 400 MA, I know what this is. What I know it is.
I wonder what the precision is of that calculation compared to the precision of the detectors.
So the question is, what is the precision of that calculation versus the precision of the detectors? And in some ways, it might normalize out because you are making the measurement of that intensity with that detector, right? So that's the data you have. And so you say, well, if I set my buttons to this and I measure an intensity out of my detector, kind of normalizes out what the sensitivity of the detector. Correct. Yeah, correct. So in a sense, I just have a big table of intensities that I've measured when I go through all these settings at that detector position, right? And so that detector position and angle will be associated with a collection in a patient later. And I know if there was no patient there, what I naught would have been measured as, right? And so you normalize to that. And that normalization or that calibration, if it's done in the fast mode, takes about 15 to 20 minutes. It steps through a lot of things to do that. And then that file is stored on the machine for that day. And every raw data set that is saved has that calibration information in the header of the raw data. So if you go to reconstruct later, you're using the calibration data for that day or a few hours ago, like not sort of general calibration for that scanner. So that's how we know what I naught should be. We also know that ID at the detector, the intensity coming out of the patient, is certainly not going to be bigger than I naught, right? It can only be attenuated. We don't generate X-rays in the patient and make them glow by stimulating some kind of output of X-rays. That's for magnetic resonance to do. Magnetic resonance, you irradiate a patient with RF, you turn that RF off, and then the patient radiates RF, right? In this case, we know that I naught is a bigger number than ID. We also know that it's essentially from point to point, just as we saw with this example. This is sort of a discrete representation of an integral through a line, right? So here you're only evaluating it for three materials, but you can imagine this as a continuous function. This is what happens, right? This solution here. So we have N naught in this slide, but I naught, and then an exponential decay that is proportional to depth, and then proportional to whatever the chemical compound is, what its linear attenuation coefficient is. So when I go through, that summation generalizes to this integral, right? So I'm going from my entry point at 0, and I'm going to essentially run an integral all the way down to D, which is down here. And it's along this line S, right? And then I add up. I do that integration of that exponential factor to get how much total attenuation occurs. Some trivial math here. I can take I naught, divide both sides by I naught, and I get ID over I naught, right? I can take the log of both sides of the equation at that point. I know that ID is smaller than I naught, so the log is going to be a negative number, right? Because this number is less than 1. So I'll put a negative sign here. This is just tradition, right? And then when I look at what happens on the other side, I've logged an exponential. And so I get essentially just the integral of all of the linear attenuation coefficients through the sample. Well, hallelujah, right? This is awesome because our image is going to be an image of linear attenuation coefficients as a function of position in the sample. That's what our picture is, right? And so bone, if it has a lot of linear attenuation coefficient, its value is high, it shows up as a bright pixel in the image. Air, which doesn't attenuate X-rays at all, basically shows up as a very dark pixel. So because mu for air is pretty well 0, right? So this is the fundamental physics of the situation. I get a value. This G value is just 1 point here, right, for this one line. But I have all of these detectors in L, and so I have a function, as a function of L for all these different detectors. And then what I'm going to do is take a whole series of those measurements with different theta values. Okay? So those are our projections that we're going to create. And again, going back to the slide that we looked at, this is a picture of G, right, as a function of L, Z, and theta. So in time, we're watching different thetas as it looks like the patient's rotating, right? But in fact, the gantry is rotating around the patient. Equivalently, you could have a chest X-ray system, and you put the patient on a spinning stand, and you could spin the patient. If they stayed still and all they did was spin, then you could make a CT of that patient, right? Just by spinning the patient. And so that's the theta dimension. And then Z is this dimension. And luckily for us, scanners now, the Z value here is like 16 centimeters, and it's divided into about 256 or 312 or 320 different pixels in that dimension. And then the L dimension is from the left to right on our screen, right? That's just the same detector moving around. And if I put my cursor there on that point, that is the same detector element, right? It's just acquiring data tick, 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 tick through time, right? This data is obtained at a reasonably fast rate. I mean, there's 1,000 projections done in about 140 milliseconds, probably, or you even more. So it's a fairly high rate of data acquisition and transfer. The entire raw data set for something that we're looking at here is about 2 gigabytes of data. Okay? And so it's not outrageous. It's not something that we need some kind of supercomputer or something. All of this works on laptops and things like that. It's okay. It's not like CERN where you're getting 3 gigabytes of data a second during a collision or something like that. But that scanner is like the size of a building. Have you ever seen pictures of the LHC or something like that? Oh, it's fantastic. It's literally, it looks like a scanner because it's all radial and it has depth. But when you look at the person next to it, I'll bring a picture next week. It's a tiny little person like this. This is a thing the size of a building, right? But it's detecting things way above 140 kVp. Okay? So it's also detecting X-rays. So here's our data, the raw data. And remember, this is from the last slide. So this is L in this direction, theta in this direction. So I have essentially a 2-dimensional data set, GL theta. This is for a single slice. We're not considering Z right now. We're just saying we'll take one of those 256 slices out and look at the 2D of that. And in that slice, which is like an axial slice, I have a two-dimensional function that is my data GL theta. And our job to reconstruct that data into a picture of the underlying object is to, find the transformation from this to the linear attenuation coefficient as a function of X and Y. And then it'll look, like somebody's heart in their chest, right? So this mapping, you can imagine now how this is being done, right? Now that deep learning and, large sort of engines and transformation engines and stuff like that are available through deep learning. If you have traditional, very good but slow methods for having a physical model for going from this to this, you only have to do that about 1,000 times, or maybe 10,000 or something. Feed that into a deep learning library and it learns how to do it, right? And it does it really well. So all of this is going to be done by deep learning stuff fairly soon. When you make this picture, which is, basically the attenuation coefficient as a function of X and Y, historically, this was done in the 70s, right? The first ones were done in the 70s. So you have a computer in the 70s, what's it got, 8 bits, if that, right? So they had to take these numbers. They couldn't put floating point numbers up there. So they scaled them. They scaled the mu values to, they took the difference of the mu value at each point from the mu value of water and divided that by water. So it was a fractional change from water. Multiply that by 1,000, right? So now you've got numbers between sort of minus 1,000 to, a few thousand, if mu is a really big number, right? So air, by definition, like mu 0, so it's minus 1,000, right? Because you assume it just doesn't absorb any X-rays. And it turns out that soft tissue in this traditional units is anywhere from minus 100 to about 60, 60 to 100, something like that. Bone gets up to 250 to 1,000, right? So it's like twice what water is. And then metals get into the upwards of 2,000. So when we put contrast into the bloodstream, the Hounsfield unit values are anywhere from 300 to 800, depending what the concentration is at that moment. When it's really high concentration, it's around 800. And then calcium, little bits of calcium for us, these are really important for heart disease. Their Hounsfield units are somewhere between 400 and 1,500. So we can look, here's our picture, right? And remember, this is mu as a function of X and Y in the plane. So it's linear attenuation coefficient. So you can see there's some things that have high attenuation. The blood with the contrast in it, blood with contrast in the descending aorta, that's calcium in the wall of the aorta. Here's bone over here. So we can put some values on here. So blood is 650, myocardium 120. This calcification was 1,300. This is an ECG lead lying on the patient's chest. It's 5,000 is the Hounsfield units, right? Think back to the formula. It's mu minus mu water divided by mu water, right? So it's, that number is 5, right? And you can see when you have something this big, it casts a shadow, right? Because this is a very high number. And so it's really hard to estimate what the true value is really close to that thing in some. So it will cast, if you go down into the noise, you'll see a lot of rays coming off this. Fat, interestingly enough, is minus 120. So it is less than, say, myocardium, which in this patient was 120. Bone is 750, skeletal muscle 105, etc. This could be 120 because perhaps some of this contrast agent has perfused into the myocardium. It was injected into this patient's cubital vein, comes into their right heart, goes to their lungs, comes back to their left heart and into the left ventricle, then up the aorta and into the coronaries, right? And when it's in the coronaries, then it goes into the tissue, right? And so the tissue should rise. The Hounsfield unit should rise if flow is okay. If you go down into the baseline and say, what's down here? You know, we've left these things that are 650, and we've gone in and put a window around stuff that's down low. So lung is about -800, right? It's not perfect air, right? Air up here is -1000, but lung has, you know, some tissue in it. And you can start to see these tiny little vessels and some fascia and things like that in the lung, right? So it's a really good technique for looking for a lung disease like water and, you know, things like that that are in the lung. And it's also really good for finding a pulmonary vein clot, right? So if you're looking for a clot in a vessel, this is a terrific way to go through and see that dark thing in a clot. Okay. So just to review, we're gonna have this data in our computer. That's what the scanner, all the detector and everything, puts that into a 2D matrix for us. And now we got to come up with a way of getting this. If you know analytically what that function is, right? So let's say it's a disk. So I have a cylinder of water. And so the cross section of that cylinder is a circle of water. And so in one dimension, I'm sorry, in 2 dimensions, I have this circle in the plane that's absorbing the X-rays as my detector goes around it, right? And we ask, well, what is GL theta under those conditions? So I actually know the equation of this bounding object. And so for a ray that comes down through here, I can just calculate this integral. It's the amount of attenuation, right, is just proportional to the length of that line, essentially. And so if I take that integral and calculate the length of that line as a function of x as I move across here, I can, for any angle here, I can figure out what GL theta is analytically, right? So now I don't have to, basically I could have noisy points along here and just fit it to this analytical function, right? And get a really nice estimate of this object. If I know a priori it's a circle. And so, it's instructive to look at what the function is, right? It's not really that trivial, right? This function as the projection of a circle, right? Oftentimes when you run a CT simulation and you're asking questions about how small a sphere can I detect with my scanner, you can run that simulation by calculating the analytical air image after it hits your object, if your object is, say, ellipsoids. So we'll put in ellipsoids, and then when I'm doing my simulation, I know precisely what the analytical function is that's going to hit my detector. So you can simulate it absolutely precisely, right? As opposed to doing it on a ray by ray simulation, which is you know, susceptible to some kind of integration errors and things like that. If I have a detector along here and I know precisely the separation of my detector elements, then I can, once I know this analytical function, I can compute the analytical intensity measured by that detector for this object. This is all before noise and things like that. And so it's often used in X-ray or CT simulations, this set of objects that are analytical. Right? And of course you can, if you just have a picture here, a really good one that you got before, you can just project things through it and calculate what the raw data would look like. That's another way of doing the simulation. We won't really talk about energy that much. I mean, we can just look at this diagram quickly, and in that, here's the X-ray photon energy. And so an X-ray, you know, what makes it an X-ray is the fact that it has about, 100 kilovolt energy when it's flying through space. And it's in this range of keV. If we turn up the voltage on our X-ray tube, we can generate, say I turn it to 120 kilovolts, then the highest energy X-ray I'm going to see is 120 keV, right? X-ray. And I'm not going to see many of them, but I'll see some. And then this curve gives the distribution of relative number of X-rays as a function of energy. So as I go down in energy, I get more and more and more X-rays coming out of this tube, relative numbers of X-rays. If this was just a target in space and there was nothing else going on, what would happen is this would just keep going up like this. But it falls away as the X-ray energy falls away, because those very low energy X-rays get absorbed by the glass in the tube, and they get absorbed by all sorts of things on their way out of the detector. And most of the time you put a piece of copper or a piece of aluminum or something right at where the X-rays are coming out to get rid of the low energy X-rays. And you want to get rid of them because they are never going to make it through the patient, ever. So they're just going to go in the patient, deposit dose, and you're never going to see a shadow. And so that doesn't seem a good use of X-rays, right? So you get rid of the ones that have no chance of getting through the patient. So if you really want to do the total simulation of what's going on, you need to know this function, which is the relative number of photons at a specific energy, and you integrate over energy, right? However, you can also just assume they're all at one energy, which is the mean of this distribution. And that's most of the time what's done, is you say, okay, I'm going to assume the mean of this distribution is like 59 keV, and that's going to be my assumption here. So when I look up the mu value of some material, I will look it up at say 59, and I'll assume that's what's happening in my scanner. Okay. So if we have these, essentially these, this 2D function, this G as a function of L and theta, how do you reconstruct the picture? So we have this, I'm sorry this turned from a G to a P, but this is for a projection. And let's say I have a very simple image. It's a 2x2 image, right? And so all I need to do is reconstruct what the mu value is for 4 locations. It's a pretty simple image. If we use this principle where a ray that's coming through here gets attenuated by the mu value in this volume and the mu value in this volume, then the projection, right, from that equation that we just saw is just the summation of those two mu values, right? This is after taking the log of the data. So then if I take a value on my detector here, say, well, what's the projection there? Well, it's the sum of mu3 and mu4, right? And now let's rotate the system, and we'll take a projection this way. This is the sum of mu1 and mu3, and I take a projection this way. This is the sum of mu2 and mu4. So I have 4 measurements that I've taken with my detector at 2 angles. I have these 2 measurements and these 2 measurements. And so that forms a system of equations, right? We have these numbers. We want to find out what these ones are, what the mu's are. We know what these projections, this is what we're finding out. So we just we write this down as a system of equations. And then you can just invert it and solve for the mu values, right? So it's a big old linear system, right? And it's that big for a 2x2 image, right? It turns out actually, if you're really good at matrices or you're really good at linear algebra, you'll look at this and say, oh, wait a minute, this matrix, it doesn't have, full rank, right? So it turns out that this one you can construct from these three, right? So if I take P1, add P2 to it, and subtract P3, that gives me P4. So I don't actually have enough information with these two views, right? So what you need is a different view. You need a P5, right? That is mu1 plus mu4 here. And with that third angle, now I have enough measurements that give me a full rank, and I can solve for these mu values. So this is a sensible way to do it if you have a relatively small number of estimates to make, right? Just inverting this big old linear system. But for, an n by n image, you will have n squared unknowns, right? And you'll have n squared equations. So this matrix becomes an n squared by n squared matrix, right? Which, for 512 by 512 is a matrix that's 250,000 by 250,000, right? So inverting a matrix that size is, especially when there's noise involved, so you have your estimates there, but there's also random noise on top of those. To get accurate or stable estimates of the mu values with this type of matrix, not a good approach, right? Doesn't usually work. So that has not been done. Well, I shouldn't say that. It has been done in some instances with very large computational resources. But a trivial way to do this, and we saw this in SPECT, right, was, well, let's take our data and just back project it, right? And, if I naively back project it, we saw what happened in SPECT, right? We got this blurry estimate of the object, right? It was a pretty good estimate, but it was a blurry estimate of the object. And so here's an example of, I have, again, three views. I've got this view on my detector, this one, and this one, right? Now I have a 3x3 picture. And the underlying truth is this, right? And when I take my data and I take this vertical orientation of my detector, so I get a 0, 3, 0 on my detector. And what I'm going to do is I don't know how this 3 gets divided up amongst these boxes. All I know is that the sum of these boxes gives me 3, right? So what we'll do is let's just take the 3, divide it evenly over those pixels, those boxes. So without any knowledge of what's going on this way, I'm just going to do that. And then I'll take the next view, right? And we'll back project, so I got a 0, a 3, a 0 this way. And I'm going to back project along here, right? And what I get, I add a 1 here, I add a 1 here, I add a 1 here, right? When I do that projection. So now I've got 1s in the corners because I had 0s there before. And I got a 2 here because there was a 1 from this projection. So now I've got this after, back projecting this view. And now we'll back project the vertical view. And now I put a 1 here, I add a 1 here and a 1 here, and I get basically where I had 0s again, I get 1s, and I get a 3 here. And we do it for this view, same thing happens, right? 1s go in the corner, another 1 here. So now I have this picture after doing that naive back projection. And it's not bad, right? Because I've got essentially a background that's flat, and I've got something that's 3 higher than the background, right? But it is not the true values that are in those boxes. And so this is just called naive back projection. I think we saw this before. If I have a profile, right? Say I have a disk, so now I have that function that was like the square root of 1 minus r squared here. And back project that, take another view, back project that, take another view, back project that. This is the underlying picture after 3 back projections. It's not bad. It shows me I've got something there, right? But obviously these are false. And after if you do that using many, many views, you get this picture, which is not exactly a disk, right? It's like a mound, right? So it actually has a peak, because these things aren't flat, right? They have a peak, and so this thing has a tippy top, a peak, and then it goes down, and it's kind of blurred. So you get a blurry picture of the underlying object. You've probably heard the term sinogram, and what a sinogram is if we take the GL theta values and we stack them, we look at the 2-dimensional function. We'll put L in this direction, so this is the detector direction, and so we plot, the G of every point along L for this specific theta. We'll call that theta 0, and then as theta goes through pi by 2 and then up to pi, we'll do exactly the same thing. We'll just plot the GL theta for those. And these data are called the sinogram. Okay. And here, this object produces a sinogram that looks like this. Okay. If you take back projections of these sinograms, so for each angle, we'll just like do exactly what we did with that simple example. We'll just divide the G value across all of the pixels in a perpendicular direction. And so one view of that looks like this, right? This is for one angle. Now I add many of these together, and this is the data that comes out. And this is called a laminogram. You can write it down as this integral here with all of these back projections at different thetas. Just integrate, add all of those up over theta, right? And it looks like this. And so you get this interesting, fuzzy, cloudy view of the object. We'll skip over that since we're late. Yeah, I don't have this. I think you're gonna probably do a problem set where you'll have in MATLAB dots is your image, so you'll have like 256 by 256 image, and there'll be one pixel that's 1, and the rest is basically background. And you ask, what does the sinogram look like for this object? And when you look at the sinogram, and there's a set of functions inside MATLAB that's built into MATLAB that takes the radon transform, and you can take a look at what the sinogram looks like for very simple objects to get an idea of what's going on. As you can see, this is the L direction along here, and this is the theta direction. And as theta drives along, you can see for a complex object like this, there's a position where all of these overlap, right? And that's right here, right? And then this one's off to the side right here when that overlap happens. But you can go through it and kind of get an idea of what it means to be a point in an image in the space of the sinogram. And what it means to be a point is basically you are a sine wave of a specific amplitude and frequency. That's kind of what I mean. Well, I should say amplitude and phase. They all have the same frequency, because right? we're going around once. So everybody's going to go through one cycle, but they'll start at different phases. So here's a simpler sinogram for, we had a very complex object with all these dots. This one's simpler, it has fewer dots. But you can see in the sinogram as we go, this looks like we're going through 360 degrees here. you know, the two major dark features, you can see the sine waves that they paint out in the sinogram as a function of viewing angle. So this is view angle this way, and this is position along our detector this way. So if I look at one location in the sinogram, so now I have a specific angle is defined by this row, and then this along the detector, this function is what we see. So you ask, well, what could be the possible angle of projection if this is my sinogram of this object, and I'm going to pick this line, say, well, what is the possible angle that could be in that object? And so there's certain features that you look at and say, okay, well, how can I work this out? If I'm projecting down from the top to the bottom and my detector's in this orientation, then the data that I see will be quite wide, right? So when I'm projecting vertically, either from the bottom to the top or the top to the bottom, I'm probably out here because it's where this gets the widest. As I go 90 degrees to that, the object narrows down to here, right? So this is a vertical projection. This is a vertical projection. So now you just have to decide, well, which side? Right? Is it on the right side going this way, left side going this way? And that kind of depends on how you want to define your, detector, the positive. If these are large positive values and this is 0, then all this trash here is the asymmetry. And there's only one asymmetry kind of in here that is dominant like that, and it's this stuff, right? And so the detector would start here, go down. This stuff would be at the high value, and the clear side would be down here at the low value. So this is probably that, with this being the high value of the detector, right? So it would be this guy. You can do that for a whole bunch of them, like saying, okay, well, what is this position where these two dark features cross? That has to be when they're lined up, right? And so that's sort of, you can play around with that. Okay. So what we're going to do is look at how filtered back projection works. So this is what we get when we do naive back projection, which is just taking these functions and pushing them back to every pixel that's perpendicular to our detector. And what's done in practice in order to reconstruct the true object is called filtered back projection. And so if this is our projection, okay, so this is going to be a disk-like object by the look of it. What you can do is, we'll just give the answer right away here, is you can take the Fourier transform of this object, and that's this function. So it's the one-dimensional Fourier transform of this object. And then you weight the coefficients of that Fourier transform by a function that just goes from 0 up to a maximum value with a linear ramp, right? So this filter is just, if this is k in cycles per meter, right? And I move away from the origin such that my amplitude here goes up linearly with k, I multiply this function by that, right? And take the inverse Fourier transform of that, I get what are called filtered projections. So they don't look like this anymore. They're filtered by this thing. And I back project those. And equivalently, because multiplication in the Fourier domain is equivalent to convolution in the spatial domain, I can take my original projection and just convolve it with the inverse Fourier transform of this, right? And then I get a convolved projection and I back project those. Both of those techniques are mathematically, turns out, are identical. to produce this back projection. When you do that, so here's our original projection. It looks very much like that projection of a disk. This turns out to be an ellipse, actually. When you take the filtered projection, it looks like this, which looks remarkably different than the actual projection itself, right? So it has a flat top, which is good because, you know, when we're projecting or when we're back projecting this function, at least we're going to generate a flat topped object, right? And it has these very steep side lobes, right, at the edge of the object. So we take these functions and back project those, and it turns out we recover the actual image. Okay? And this is called filtered back projection. So this is, remember our complex object that had all those little dots. This is the sinogram. When I take a back projection of that sinogram, or if I look at the values in that sinogram, it looks like this. Remember, all those G values are positive. When I convolve it with this thing, okay, it produces this new filtered sinogram. And so now, as you can see, it goes between 0, or it basically has a mean value of 0, and it goes positive and negative. And these are the things I'm going to back project. And so they look like this. And then as I put more of them together, if I put, say, 40 of them in a projection, it looks like that, 80, 120. And then finally, when I'm done my 240, I get the object back. Okay. And so let's watch how this happens in a head scan. So this is a back projection sort of in real time of how the CT head is generated, right? So as you're adding these things up, this is the result of that sum as you're adding more and more of them together, right? So you can see, like, as we move along here, I have really good edge data here. Like, so perpendicular, these are obviously back projecting this way because perpendicular to this line, I have really good information about where this edge is and good information about where that edge is. I have absolutely no information in this direction, right? So everything gets spread out in that direction. In order to get that information, I need projections that are orthogonal like that to get that information, right? So as you can see, we're sort of painting, we're going around the object and we're painting edges that are perpendicular to our projection direction. Okay, I think in the lecture, if it's not there, I'll put a program in that you can play around with the radon transform, which is basically creates from an object, it will create the raw data of this object, the projection data of this object. And then you can do things like, well, what happens if I used half of that data to reconstruct a CT picture? And I could use half of it by like cutting half of it off. So I just sample for half the time, and you look and see what the resulting image is. Or I could sample, you know, every other view or every fourth view and see what the picture looks like under those conditions. So you can just get to know the radon transformation.